Welcome back. We're going to be looking at pointers and typing, and something that's dear to your heart. You're using it very often in other languages. We have to take a close look at it, and you're going to see real quick that this is something that's quite delicate, and we've got to be careful. So C++ is a strongly typed language. Unlike C, and especially when we're talking about pointers, C++ pointers are strongly typed. What do we mean by that? Is that if you have a pointer to a character, you cannot, the very next second, see it as a pointer to an integer and make use of it. If you think about it, it makes sense, because a pointer to a character is a pointer to a memory block whose size is exactly 1 byte. If you see it as a pointer to an integer, you will get the pointer to a memory block at the same memory location, but whose size is 4 bytes. So if you were to write an integer into this, you would overwrite the first byte, okay, but then you would also overwrite bytes 2, 3, and 4 that do not belong to you. You would be overwriting memory that's not yours to play with, and that would lead to a memory corruption and crashes of the most horrific form. So you don't want to do that. And the big corollary is that to avoid issues, unlike C, C++ is strongly typed, and it says your pointers have types and you have to abide by those when you're manipulating pointers. You can't, what we call, coerce and force a pointer to one type to become a pointer to another type. Now, that sounds a little restrictive. It sounds a little Java-esque on the side, because, well, the whole point of C and C++ is you're the king, you're God, you do whatever you want. You manipulate those pointers in however way you feel like. So yes, C++ is strongly typed, but there is an escape route. There is always a way to revert back to the C style of doing things and to really cast pointers. It's just that C++ provides you with a structured way to do that. They provide support so that the most horrific bugs can be avoided when you actually end up truly using casting. So in C++, casting the way that you learned to do it in C is really frowned upon. You shouldn't be doing that. There is a much better way using one of the C++ mechanisms. So in C++, there are 4 ways to cast, no less, 4. Static cast, const cast, reinterpret cast, and dynamic cast. In C, there is only one way, which is what you see here, which is if you have an expression, you parenthesize it, you put in front of your expression a cast to the type you wish. So for example, your expression evaluates to a character pointer, you want to see it as a float pointer, then you write float star in between parentheses and you parenthesize the whole thing, and there it is. C lets you see your pointer to character as a pointer to a float, no questions asked. That's the end of the story for C. C++, you have all these mechanisms and they have different semantics. So let's review them one at a time to really appreciate what they do. So the first and most innocuous one is called static cast, and its point is to convert between compatible types. So if you have 2 compatible types, you can convert between them in a meaningful fashion. Note that the check is done at compile time. The compiler is going to verify that what you claim are compatible types are indeed compatible, and if that's the case, he will let you do it. If they're incompatible, he will scream. So here is a simple program that we get here. We are basically defining x as an integer whose value is 10, c as a character whose value is a, and then we do this funny thing. We take the address of C. Now, you've already seen that. It means that we're manufacturing a pointer to a character. And since both X and C are on the stack, and you even know how they are laid out, we know that C is underneath. This is clearly a pointer to a character, and we could override that character and use it. But rather than doing that, we static cast that pointer to a character into a pointer to integer. So we do exactly the example I described a second ago. And I get back, as the result of the static cast function, I get back p, which is a pointer to an integer. So the question, of course, is what does that do? What's going to happen if we try that program? And we can give it a quick try and see the effect of this. So let's go in the editor, and I'm going to retype that real quick. We should actually load the file. Actually, I might even have the file, pcast. No, okay. Yeah, so I have files like that. So I'm going to create a CCast1, and I'm going to retype that guy. If I can type correctly. So this is something that you can always do to learn a language, is to play with the various construction and see how they respond to you with small programs that are harmless to really appreciate the semantics of those. So this is my program. It's called CCast1. So I'm going to go in a shell, and I'm going to say C++ CCast1 minus O CCast minus testd C++ 14. I compile that, and here we go. We get back a type error, and he's telling me static cast error. You're converting from char star to int star, and that is not allowed. That's exactly the example I was describing. It would be insane to use P to read, because you would be reading bytes of C and bytes of X, kind of an hybrid, and writing to it, you would be destroying the value of X. So this is definitely not safe semantics. So the compiler catches that. Note that if you were using the C-style cast, you could. And C++ would actually tolerate that and let you do this. That's why I'm saying that C-style casts are frowned upon. The compiler does not prevent them. You can use them, but you get zero protection. Here with static cast, you do get protection, and if you try something that's really iffy, the compiler will tell you, I don't think that this is sensible. So you're probably wondering, well, when do I actually use static cast? Well, you can use it in a number of circumstances, especially with objects and pointer to objects. So if you have a class hierarchy with two classes, A and B inheriting from A, you have a pointer to a B that you're currently seeing as a pointer to an A, you could use casting. And in Java, we call those downcasting. That's what static cast is really for. We'll see examples of that. We'll revisit static cast when we get to classes to really see a natural example of its use. But you can use it on numeric type as well that are compatible. Good. So that's what's happening here. So now, let's go on and take a look at the next victim, const cast. So const cast, the whole idea is I want to change the constness of a program of a variable I've already declared somewhere. So again, let's look at this. And again, it's done at compile time. Let's look at this simple program. I have x, which is a constant integer, right? So x is an int, and it happens to be constant. And now I'm using a const cast to obtain an int pointer. Well, let's think about this. Is it really sensible? If I was just using %x, what would be the type of that? Well, if x is an integer that happens to be constant, %x is a pointer to an integer that happens to be constant. So it would be a pointer to an integer that's constant. And here I'm asking, no. I want to see that as a pointer to an integer so that I can, well, God forbid, overwrite to it. And I get back p, which is a plain pointer to an integer, which means I could actually make an assignment. I could write star p equal 20. And since p is a pointer to an integer, well, that should be authorized. I can write to such a thing. And of course, you see that what I'm doing afterwards is I'm printing p, I'm printing the address of x, I'm printing x, and I'm printing what's pointed to by p. Well, let's see what happens when we try and run this program. So we're going to log, and this time this is ccast. Right? This is exactly the program we were dealing with. Let's reindent it nicely. We are dealing with an integer that happens to be 10. We're doing a const cast. Then we're writing the value 20 to it. And then we are actually printing out. And let's indent everything so that it looks clean. Okay? So now I'm going to go inside the shell. And I'm going to use my trusty compiler to recompile that program, and I'm going to run it. And we see something interesting. So you have the program above, you have its behavior down here, right? So the first thing is no compilation error. So all of this is okay. So I could strip away the constness from the pointer. Note that it works in both directions. You can strip away the constness of a pointer, or you can add constness on top of a pointer. It's perfectly fine. Usually the constcast is used to strip it away. Once that is done, what do I see? I see P, my pointer, and we see that the address is 79A8. That's the address I'm getting back for P. P, which is the result of the const cast. Now, if we ask what is the address of X, well, it's CF79A8, right? It's a little small for me, but you should be able to see this. Clearly, the address of X is the same as P. Now, what I do after that, the next print, and this is the print that happened after reassigning star P to 20, if I look at X, I get the value 10. That's interesting. My X hasn't changed. Now, if I ask to print what is pointed by P, that is where P is my integer pointer, I'm getting back the value 20. So the assignment succeeded, but somehow the pointer is different in both cases. And that's what makes the difference between these two statements. So you see really that here, my X, which was constant, hasn't really been modified by this statement. And we have to keep that in mind when we're seeing what we're doing with stripping away this constnet information. So that was constcast. If we look at the next one is known as reinterpret cast. And here the purpose is to do the ugly thing that C was allowing you to do. So that C cast, if you want to actually use it, don't use the C cast. Use reinterpret cast instead. This one will let you do whatever you please. It will convert between incompatible type, and of course it doesn't check anything. It behaves like C, there are no checks whatsoever. What happens is that the pointer is copied bit for bit from the source to the destination with no attempt at understanding what is going on, and we're getting, as a result, a pointer that we can use with the right type. If it points to the right thing and all makes sense from a memory standpoint, it's going to be okay. If it doesn't, well, tough luck. It's just like C, you're going to corrupt memory, and I hope that you know what you're doing. So bottom line, this is extremely dangerous. You should refrain from doing these sort of things, and if you do, it's imperative that you have a clean mental model of how the memory structure of a C or a C++ program operates to actually make sense out of this. Dynamic cast is the last partner in crime, and this one is meant to actually convert between objects of different types that belong to the same hierarchy. It's to do the downcast, but it happens at runtime. Unlike static cast that verifies that the cast makes sense at compile time, this one makes sure that the cast makes sense at runtime. Now you tell me, if at runtime the cast doesn't make sense, what happens? Well, nothing too bad. Dynamic cast returns the null pointer. It will return a pointer that's 0 so that you cannot dereference the thing since the cast made no sense. So you can always dynamic cast, check the result of the dynamic cast. If it's null, well, you know that it was not a valid cast and your program should be ready to deal with that. And if it was non-null, then you have the right object and you can start manipulating it. That's it. That's the whole story on our cast, and we'll attack the next module next time. See you shortly.